Intelligent Transportation Systems podcast. Congratulations to everyone! This is our second anniversary episode. We have 24 episodes online and this is our 25th. I'm Javier Sánchez Medina from the IEEE Intelligent Transportation Systems Society. We have prepared a special episode to celebrate this milestone. We have a different news mini-section where Dr. Maryam Kaveshgar will summarize some of the most outstanding achievements we have witnessed in intelligent transportation in the last 2 years, since this publication exists. Then Mehran Shirazi will introduce a new mini-section called Amazing Transportation, where he will be talking about some rather unusual yet surprising jobs related to transportation. Don't miss this one, it's hilarious. We also have a very illustrative interview with Dr. Wagner about SUMO, a brand new approach to traffic simulation very much in line of an open software philosophy. We have worked very hard to get this party ready for our listeners, our special, unique, distinguished community that we treasure. Thanks for being there. Let's start now, have fun!
Hi, this is Maryam Kaveshgar. Welcome to our second anniversary episode. We have made 2 years online with our ITSPodcast since May 2013. During this time, we have had a lot of amazing advancements in intelligent transportation systems all around the globe. To name a few, we have made impressive steps forward regarding automated driving. We have come from some 90% of performance in automated driving to 100%. We have witnessed some fascinating driverless demonstrations like on 12th July 2013, Parma, Italy, an autonomous car successfully drove all the way through the rural roads, freeways, pedestrian crossings, traffic signals and roundabouts autonomously. It was Wislab's car proud. Many sensors were integrated deep inside the chassis, including 2 frontal cameras, lateral cameras, and 2 lateral laser scanners, a frontal laser scanner, and 2 backward-looking cameras. It was fascinating. The following month, Mercedes-Benz tested its autonomous car on the same historic route which was once taken by Bertha Benz. Once more, Mercedes-Benz proved its spectacular engineering achievements. Developed on the basis of the new Mercedes-Benz S-Class, the S500 Intelligent Drive research vehicle autonomously covered approximately 100 kilometers with the aid of its highly automated route pilot. The vehicle is able to negotiate its own way through dense traffic and complex traffic situations. In 2012, Volvo had already started a very interesting concept of platooning, and by April 2014, Volvo's autonomous cars were already rolling around the Swedish city of Gothenburg. Volvo has called its system the autopilot. The system uses radar, camera, lidar technology, and a map of the route. They have promised to bring 100 cars with the autopilot system to the streets of Gothenburg by 2017. Although Google had its driverless car on the road from 2011, but it started to introduce its own pods in May 2014, and by December they decided to make them roadworthy by adding headlights, steering wheel, and pedals. Till that time, they had only buttons to control them. The Lutz Pathfinder in the UK was a response to Google's pod. It was unveiled in February 2015 and was the first autonomous car which was allowed to run on the public paths in the UK. In March this year, a customized Audi SQ5 made autonomous by a British company, Delphi, made the first cross-country trip in the US, traveling from West Coast to the East Coast, from San Francisco to New York. The car dealt with roundabouts, bridges, roadworks, tunnels, and aggressive drivers through a range of weather conditions. We also heard statements and declarations made by many car makers about their nearby horizons when they will be selling autonomous cars. GM team announced that they are open to work with Google for developing self-driving cars. Besides autonomous driving, we have had many other astonishing milestones. We have enjoyed impressive advances in V2X technologies, including vehicle-to-pedestrian, vehicle-to-bicycle, vehicle-to-vehicle, and etc. Because of that, information and communication security has become more and more important. Automated parking started hitting the market. We have seen an incredible evolution in driver assistance systems, including emergency braking and evasive steering for pedestrians, steering assistance, night vision, collision warning, advanced cruise control systems, and a few others. Sensors technology has improved a lot as well. Unmanned aircraft systems, UAS, or drones have become the next big thing. FAA designated 6 test sites around the US to legally operate. Many big companies like Amazon and DHL claiming they want to use them for delivery services. DJI Phantom 2 being the popular one. NVIDIA in the business of automotive processors and their convolution neural networks. The CNNs have blown away competition in object recognition, and with GPUs, they can be trained without a supercomputer. CNNs are looking to solve all our machine learning problems. US Department of Transportation launched Connected Vehicle Safety Pilot with University of Michigan's Transportation Research Institute back in 2012. The information collected by NHTSA will make V2V communication part of rulemaking. Rear-view backup camera will be standard equipment in the US by 2016. Autonomous and driverless cars were the hit at CES 2015. US will emphasize pedestrian and bicycle safety. So, what will happen in the next 2 years? Some colleagues gave us the following hints. We are on the brink of bringing low-speed automated driving and automated highway driving to the market. We will see more and more new research talking about relationship of ethics and mobility, where some colleagues are already doing cost-benefit analysis for transport policy options from an ethical perspective. We will hear of crowd engineering, a brand new way to develop big projects, and lots more that you can be sure that will keep you posted. Please continue to follow us.
Amazing Transportation by Mehran Shirazi, PhD candidate at Simon Fraser University, Canada. Unique transportation jobs that exist only in some countries in the world. 1. Professional license plate obscurer, Tehran, Iran. Air pollution and congestion restriction have resulted in a rule which states that each car can travel to downtown Tehran only on certain days of the week. The days are different for cars with odd and even license plate numbers. However, you can pay some professionals who run or ride a motorcycle behind your car and block your license plate where there are cameras. 2. Extra passengers, Jakarta, Indonesia. There are some zones in Jakarta which requires each car to always have at least 3 passengers. You can pay some people named Jockey to be your extra passengers. 3. Insurance companies for ticketless travel, Mumbai, India. The Mumbai local train network serves about 6 million passengers each day. Since checking everyone for ticket is not possible, there are only random checks. Ticketless travelers can buy insurance from some companies which pay the fine if these ticketless passengers are caught. 4. Subway pushers, Tokyo, Japan. Tokyo has one of the most crowded subways in the world. Oshiya, or pushers, push the passengers inside the train so that the doors can be closed. 5. Traffic zebra, Bolivia. Young people who need money towards education, former drug addicts, and at-risk young people are hired by government to wear zebra costumes and reinforce pedestrian and car safety at intersections. 6. Seat fillers, Kenya. Passengers are not eager to buy bus tickets if the bus is not ready to leave. Seat fillers are paid to sit in the bus and create the illusion that the bus is almost full, ready to depart. This encourages more people to buy bus tickets quickly. 7. Flying doctors, Australia. Australia is so large and its population is so small that many people have to drive more than a day to arrive at a hospital. In 1928, John Flynn pioneered the idea of an aerial doctor service who could attend to patients in far locations. It still operates today. Do you know any other transportation jobs that are specific to your country? Let us know.
Hello! You probably know that sumo is more than a traditional Japanese sport. Are you ready for the main content of this special episode? We have Dr. Wagner, a physicist that founded that very trendy new traffic simulation platform. Let's learn about that.
We are today with Peter Wagner. As a researcher, Dr. Wagner held various positions in universities and research institutions. Dr. Wagner has been with the German Aerospace Center since 1996, where he joined the Institute of Transport Research by 2006 and became a chief engineer by 2008. By the end of 2013, Dr. Wagner has been appointed as the honorary professor of dynamic modeling and control of transport systems by the Technical University of Berlin, where he has been lecturing since 2003. Dr. Wagner has a long experience in modeling and simulation of traffic flow and in part has been working for the open source project Simulation of Urban Mobility SUMO. Hello Peter, can you please introduce yourself to our audience?
Hello Hilmi. Before starting, let me express many thanks for the opportunity to present our work here. My name is Peter Wagner and I'm a physicist by training. Especially theoretical physicists like me are specialized in doing modeling work, and this is what attracted me to the field of traffic and transportation in the first place. Meanwhile, I love especially the exciting and sometimes challenging interface between the more theoretical part and the translation into practice, and something that really works in the real world.
Thank you, Peter. Can you please tell us about the focus, research areas and the scientist profile of your team at the Institute of Transport Research at German Aerospace Center and the recent projects that you have been conducting and contributing to?
The main focus within the division I'm working is on traffic management. We try to cover the whole process from traffic surveillance to making use of the data, model and simulate the system behind, to finally finding means into action, that means trying to influence traffic. This can be done either by looking into traffic control more deeply, and this is of course where SUMO can help a lot. There are a couple of projects we are doing with SUMO, but right now I want to mention just two of them. In Wagner, we are working on the topic of disaster management, and we are working together with German authorities who are responsible for this. Of course, our part is to help with the surveillance part, which in this case is an endeavor which involves also other DLR institutes, in order to do this from the air or even from space. And our division is working on the logistics of it, and of course on the traffic part. The problem we would like to solve is how can we bring the needed relief forces to the place where they are needed, while keeping traffic flowing as much as possible around this disaster or even the big event. Quite on the other side is a smaller project called Vital. Vital is on traffic control of individual signals, and the principal idea is what we found a couple of years ago. We found a nice way how to control the traffic light when you do not have loop detectors but only vehicles communicating some information. We have earned a couple of patents on this, and now we try to put this into the field. Of course, we have tested it with SUMO, and in SUMO anything seems to work fine. Well, but you know, this was a simulation. And now we have the chance of looking into a real field test, and as usually nothing is as simple as it appears to be in the simulated world. For instance, we were talking about connected cars and car-to-car and car-to-infrastructure for a very long time. For this field test, we do not have it. And that means that in order to somehow make it, we need to emulate, in a certain sense, car-to-car communication, and this, of course, is being done with a lot of normal or classical loop detector devices and something like that.
Okay, thank you. SUMO is not just another traffic simulation framework, actually. It is more like a brand new paradigm of traffic simulation, contaminated by the venom of openness, international collaboration and development. I believe this approach is very much resembling the usual open software development approach, with some pros and cons of open software, of course. I mean, on one hand, you will not probably become rich off the royalties of this software, but on the other hand, the growing and very active SUMO user community, helping to spread its implementation everywhere, has been reporting you and your group remarkable prestige in this field. But why did you create it like this in the beginning? I mean, has the astonishing spread of the tool caught you by surprise?
Well, SUMO has been started shortly after this institute has been created, and that was in 1999. And originally we had the idea of doing it open source because we want to offer something to especially the German community. Of course, open source, in my view, is something that is truly international. Therefore, we never ever had even the idea that it should be restricted to Germany. And of course, in the beginning, we were not exactly clear that it was a good way to do it and precisely how to do it. That was one point. The second point behind SUMO was that I think that traffic is very often not very well understood. And therefore, I had the idea that working with SUMO and developing SUMO itself, it helped us very much in building a clear idea how traffic works. As a physicist, you may know that I always have the idea, if you have something programmed, then you have understood it. Meanwhile, I have learned that even this is not true in any case. You can't even program something without understanding it, and vice versa. And when we look at our mailing list, such a software has a tendency to make it too easy for people to get started, since it gets you started too fast for a thorough understanding of what's going on there. By the way, people who are not used to writing software, at least on a very basic level, would strongly deny that getting something started with SUMO is easy. Because they always have difficulties in starting it at all. Of course, the usual ideas behind open source apply to SUMO as well. That means we would like to build a platform where the whole community can implement and test their models and implementations. And of course, we would like to set up a standard environment to make implementations of models, but also different intelligent transportation system measures comparable. That leaves me with the final part of the question, success. We definitely are pretty much happy that it happens. That means that so many people are considering SUMO and try it out. We have discussed here, was it a surprise or not? I personally think definitely it is a surprise, because originally the idea was, oh well, there will be only very few people who will actually trying it out. Of course, there is another problem, or let's say a dark side to it. That means if we would like to give support to a growing community of users, especially take into account that very, very often people use SUMO only for short-term projects, such as master thesis and the like, is sometimes pretty hard, because we need a lot of work putting into it and trying to help people. And for this, the SUMO team is a little bit too small, so we sometimes fail there a little bit.
Okay, thank you. Can you please mention some examples illustrating the range of applications in ITS where SUMO has been proven useful? What is the most exciting and maybe unexpected application you have seen?
To start with the last one, the most exciting is definitely what I said just a couple of questions ago. This project named Vital, where we try to put something into real life that has been tested with SUMO. Of course, we started SUMO with a little bit different idea, and the first applications we had in mind was a simulation of complete cities for getting travel times and for implementing something like a microscopic demand model. And though SUMO it definitely comes from this direction, and that means this field of application has had a major influence on SUMO, and I think it is one of the reasons why SUMO is so widely applicable. Trying to simulate big areas at a fast speed is keeping your eyes open at performance. And as soon as you are able to simulate big areas in good quality, you can do the same for smaller parts of the road network as well. Well, I think since these last 15 years or so, we have done a lot of projects, and I think at least part of them are listed on our webpage. So I think there's no need to go into each of that into detail. The main point is that we still can run really large scale scenarios with large scale routing applications, that we can forecast this event traffic. Remember, I talked about this Wagner project where we try to forecast what's going to happen in the event of disaster management or something like that. And of course we have used it to simulate communication scenarios between vehicles. That was an interesting point. Yeah. And it is one of the main point where SUMO is being used. There is a big acceptance within this vehicular communication community, which is mainly being conducted. Well, that's the problem I talked about already, from non-transport engineers, but rather from information scientists or traffic engineers. Yeah. And it seems that about 27% of SUMO's users and SUMO applications are coming from this community. But my feeling is that it's changing now a little bit, but well, that's it for the moment. And but in addition, we have only a limited view of what users are using SUMO for because they do not, in each case, tell us about.
Okay. One can use SUMO as it comes out of the box, or one can customize it far beyond. For example, creating disruptive vehicles that don't obey traffic rules, or platoon of vehicles circulating in a group way closer to each other than the default SUMO safety distance setup that's set up. Do you believe that the success of SUMO is due to its flexibility?
Well, it's a bit difficult to say this is exactly hinging on this point or so, but what is for sure is that the flexibility of SUMO is, of course, an asset, and especially concerning the more IT-affine community. And of course, at least in our view, the biggest match winner in this regard is Tracy, which is a shortcut for the traffic control interface. After introducing the Tracy API, that allows to control the behavior of the simulation instances from outside by self-written applications, either in Python or MATLAB or whatever, users neither have to use a specific language nor to get common to SUMO's internals. The coverage of Tracy allows to control almost everything that happens within the simulation using the paradigms and programming languages one is common to. But still we get, from time to time, questions, does this or that work in Tracy? And we have to answer, not anything works in Tracy. Still, there is more than the pure flexibility of the software. Almost everything that was used in our own research was inserted into the publicly available version as well. And in fact, usually we only work with the public version. But all these projects, they have introduced a large variety of different models. For instance, SUMO can have, I think, 8 or 10 different car following models, output types, and all these, in a certain sense, helps in covering many different needs and many different applications.
Okay, so how about its performance? Have you done any comparative evaluation considering the well-knowns in the field like Aimson, Mitsim, Dracula or others?
No, we have not. But of course we have looked into SUMO itself with sometimes, let's say, disappointing results. For instance, when I personally write a piece of code that simulates an intersection or a piece of freeway, this can be 10 times or even 100 times as fast as SUMO. So of course we have done a lot of profiling and looked into SUMO. Why is it so much, let's say, slower than some specialized code? And the answer is very simple. SUMO, and I think this is the same for any other microsimulation as well, it needs a lot of time in order just to perform the organization of the vehicles. The vehicle dynamics, this is just 10 or 15% of the total time that the simulation in the SUMO needs. And all the other time is spent on organized things, for instance, the priority questions, the traffic lights, the routing, and how to insert vehicles. All these kind of things, they take up many of the time. And again, this is pretty much the same for all the other simulators around. So my basic feeling, but again, we have not done any real benchmarking, is that SUMO is a little bit faster, but of course its performance is not orders of magnitude better than anything else.
Okay, now let's have a short break.
Hi there! The Intelligent Transportation Systems Society has now its own Twitter, Facebook, LinkedIn and Google Plus accounts. We want to invite our followers to join us there. It's easy, you only have to search for ITSS.IEEE. ITSS, as in Intelligent Transportation Systems Society, .IEEE, as in IEEE. We will publish there all the ITS podcast news and much more. Please check it out. Let's get back to our today's interview.
We are back with Peter Wagner. Today there exist numerous variants of micro, meso and macro level traffic flow models and rapidly progressing high-performance computing facilities. I know that you have also conducted research at the Center for Parallel Computing at the University of Köln. According to the state of the art and today's technology, can you please share with our listeners what an advanced traffic simulation model should be capable of?
One should say that the currently available simulations are advanced already. Rather, some topics and even subtopics should be focused more in the future. This mainly includes improvements in the car falling and lane changing models that are still hardly replicating correct stop dynamics or other things. As well, safety-related measures are currently badly covered by microscopic models, and some work should be done here. And of course, as you might have recognized already, performance is still an issue since we are heading into even larger scenarios with ever increasing level of detail. Part of this can be handled by parallelization, so we have this on our agenda, but it is very often but in the back because there are other more pressing issues.
Okay. I know there are quite few of young researcher comparative studies out there, and for probably many of them, they picked SUMO. What is the most frequent reason you have heard? I say young researchers, meaning researchers with an open mind to any of available tools. You know, sometimes our colleagues just use the tool that their group has been using for years.
We have done nothing systematic in this kind, so I can only report a few things which my colleagues have sampled. Of course, you have the usual suspects. That means SUMO presents a low entry barrier. That means you have no costs. There are tutorials available, so you can try to learn it by yourself. And if you have an open mind for IT, then you will learn it relatively easy and relatively fast. Then, of course, there is an active community of people who can answer questions. And, of course, finally, as usual with open source, there is the extensibility. That means, in a certain sense, you can extend it, and some people have done that. Sometimes we have learned about that, but I'm sure that quite more often we have not learned about people who have extended SUMO in a certain direction. And of course, you might recognize that there is a slight downside to this. One of my colleagues once phrased it in a beautiful manner. He says, some people believe that SUMO is still lacking the deliver my thesis fast button.
Okay. How would you say SUMO-based developments fit real-time traffic control challenges? Marcos Papageorgiou mentioned in a previous episode that it is very different problem to solve when you are using a simulation tool, for example, for planning purposes, than real-time traffic management. Do you think SUMO may also fit real-time constraints?
Wisely, this depends on the size of the system and what exactly you want to do. The applications I know of mostly use such a simulation just to reconstruct or even to forecast the current state of traffic. And even this is tough work because I have mentioned it already, since real nets are large, they are complicated, in a certain sense they are dirty, because you have to put a lot of work into it to make them sustaining a micro-simulation. And finally, when we compare the simulated drivers with the real one, it seems that the real drivers have more flexibility than what our modeling assumes. And even in this case, so that means we can do this simulation only to a certain approximation, and how to get rid of all these dirty details has not been solved yet in a satisfactory manner. I think this will become better in the coming years because all the input data will become better. But right now we are very often deal with the data and not with the model itself, which is a pity. Well, the second question is, of course, which kind of traffic control do we talk about? For instance, it is well possible to change traffic light programs on the basis of a simulation and even on the basis of a forecast. This is a process that is comparatively slow. It means those programs of the traffic lights, they are changed, let's say, any 15 minutes or so, something like that. It is definitely much harder to give each traffic light in a large network the precise moment when to switch the phase on the basis of a simulation. This will work only for small instances, at least right now. However, in the already mentioned project Vital, we are doing something similar. But this is, again, just one intersection. And one of the methods we have implemented there, this method needs a forecast and a precise forecast for the next minute or so. And this forecast, and it is needed not just once, it needs this forecast for different configurations. That means for different switching times from red to green or something like that. And this forecast is, of course, based on the input of the detectors that we have, and it is based on the precise policy. And so we need to run many SUMO simulations during just, let's say, 1 second in order to find out when will be the best next moment to switch a traffic light. Well, this is really challenging, but we can do it. So, as I told you, if you have, let's say, 1 or 2 intersections in mind, that might work in real time. But if you have a really large network that you would like to control in every second, then Marcos Papageorgiou is in fact right, and this cannot be done, at least not with SUMO.
So, what's the future of SUMO? I mean, what are your plans regarding this nice piece of software?
In any case, we have to have an eye on new projects and what they request from us. And with new projects, I mean especially the projects that come from our institution. And of course, apart from this, or maybe even in line with this, there exists a kind of wish list. And of course, this wish list is very long if you go into details, but it just give you here the most important point. That is, we would like to have a better grip on intermodality, because we think that is one of the main future focuses. We would like to improve how easy it is to use SUMO. We would like to make it faster, as I told already. And there's another point that is we would like to shorten the list of bugs. It means that we'd like to improve the quality.
So, as far as I know, you'll lecture a tutorial on SUMO at the forthcoming IEEE Intelligent Transportation Systems Conference that will be held in the Canary Islands in September. Who do you think should attend this tutorial, and what may its participants expect?
This tutorial is mainly targeted at newcomers, but it teaches also advanced features such as person modeling or intermodality as far as they are right now implemented in SUMO. And it is a little bit based, but not completely, on material which is given in my course at the Technical University of Berlin. But in addition to that, we have given this material also already to other people as well.
Thank you, Peter. Finally, what do you suggest to our listeners, especially the young ones, that try to contribute to the state of the art on the modeling and control of traffic flow?
Okay, there are two things I would like to mention. The first and most important one is try to contribute to SUMO. The second one is look at our situation and in fact it is so that I have a boss and he would very much love to see that we are invited in a project where we can develop SUMO further. And this is, of course, in line with creating funding opportunities for our institute. As we might know, SUMO is right now well integrated into our internal R&D endeavor, but having additional external funding would ease internal discussions and promote SUMO's development and maintenance.
Thank you, Peter. Thanks for your time. I also want to thank you on behalf of the management of the IEEE ITSPodcast. Thank you and see you.
Yeah, thank you, Hilmi. Bye-bye.
Bye.
Well, we're now reaching to the end of this episode. It's incredible how fast time goes by. We feel it's an amazing adventure to have the honor of talking to this unique community, conveying the latest and hottest in our field, especially in these days we live. Thank you very much. Please keep on pushing. This podcast is sponsored by the IEEE Intelligent Transportation Systems Society, website designed and managed by the Innovation Center for the Information Society at the University of Las Palmas de Gran Canaria in Spain. Soundtrack developed by Rubicon, language advisory by Emmanuel Larvelo and Professor Son Williams from Clemson University, South Carolina. The initial Happy Birthday adaptation was performed by the Chamber Orchestra Kremlin, conducted by Misha Rachlevsky. We'll be back soon bringing you again the cutting edge of science at the Intelligent Transportation Systems podcast. Thanks for listening and drive safe.